Hello and welcome. My name is Theo, and this is an investigation into the low gravity dynamics of a vortical interface. By vortical, we mean having to do with a vortex or a rotating flow. And by interface, I mean the boundary between gas and liquid. So why do we care about gases and liquids in low gravity? Here you can see a mixed phase, which is to say liquid and gas blob, bubble and drop combination on the space station. There's an Alka-Seltzer tablet inserted into colored water. And you'll notice that you'll notice the presence of both gas and liquid together because the lack of gravity means there's no buoyant force to separate the gas from the liquid on the space station. Here's another example, again, from the space station, where the bubbles inside the water have no reason, there's no dominant force for them to separate from the liquid phase. And this presents a big challenge for a variety of space fluid systems. Pumps and turbines and many other types of fluid components expect to see single phase flow in either the gas or liquid state. And so the lack of buoyancy and therefore the combination of these phases presents a great challenge for a wide variety of fluid components. The vortical phase separator is one phase separation architecture, which doesn't require the presence of membranes to separate gas from liquid, nor does it require power except for the pressure drop through the device. And so it was proposed in the 60s and studied then as a relatively simple method to separate the gas from the liquid phase. And here you can see it essentially consists of a laser pointer here, the injection of the two-phase mixture tangentially into a tank, which uses the fluid momentum to generate a vortex. And then the difference in the densities of the bubbles and the liquid phases induces a centripetal buoyant force on the bubbles. So they rise, so to speak, toward the interior where there's a gas core created. And the gas can be extracted through the gas outlet at the bottom and the liquid through the bottom at the outer tank wall. And so when this device is disturbed in some way, we expect the interface to form some shape, which will be a superposition of vibration sinusoids. And this is fine unless this disturbance creates one of these failure modes where either the liquid is going out the gas outlet or the gas out the liquid exit. And in particularly egregious cases, the liquid can even bridge the entire gas column, which would present another failure of the device, because we want to make sure that we're getting pure gas or pure liquid and not a mixture of the two. So where is this useful? In any of the on-orbit activities, such as washing or hygiene, or any number of fluid systems which have both gas and liquid phases, or on a larger scale, propellant depots, where there will be some liquid and gas phases present together in a tank, which will not be separated by a bladder. So we want to make sure that we know that if we are interested in getting either gas or liquid, that we're going to get only that phase. And a vortical phase separator in either of these scenarios could be very useful in ensuring that phase separation. The vortex phase separator has been investigated on parabolic plane flights, although it has not been flown in space. You can see here an investigation in the early 2000s into various types of failures, which could be present. And then this was an investigation into the transient behavior as well as steady state with startup and shutdown of the device. Notably, however, the dynamics of that liquid gas interface have not been investigated in depth. And so this study aims to validate a model for the performance of that gas-liquid interface based on the dynamic response to perturbations. So our goal here is to establish a vortex, which we'll do through very simply rotating a tank on a parabolic plane flight, measure the dynamic response, and then compare that response to the analytical sloshing solution. So here's the payload to do just that, the Vortical Interfaces and Sloshing and Axisymmetric Tanks, or VISAT payload. There's a lot going on here, but the main the center of this device is this rotating tank with cameras both radial, viewing it radially and axially from the end here. The rotation is accomplished through the rotation servo, which is geared to the shaft of the tank, and then the perturbation servo, which will slide the entire rotating tank assembly along a track, which is at the bottom of the payload. Here's what it looks like integrated. You'll notice the radial and axial cameras here, the tank with colored water in the center, and then the servos both for rotation and for perturbation on the sides. Altogether, it looks a little bit like the payload version of a circus act, but this was what was required to both establish a vortex when we are in the parabolic plane, as well as to perturb that interface with the axial input sliding along the track. Here is video from the plane flight. This is viewing, you can essentially think of it as through the side of a water bottle, which is being swirled like this. You'll notice that before the microgravity, or low gravity rather, section of the flight starts, we have the paraboloid that we would expect. And then as the plane enters the parabola, so going up and then back down again, that paraboloid gives way to a cylinder because the gravitational term is no longer present, and so the centripetal term takes over. And here you see the onset of perturbations by the sliding along that track. We wanted to make sure that we established the steady state cylinder before starting the perturbations. And then at the end, you'll notice that the presence of the gravity potential enters back again, because you can see that that cylinder gives way to the paraboloid. So here's what tracking of the interface looks like. This has been slowed down 10 times, and you'll notice that as the perturbations begin, every pixel row in the video of that interface is being logged as sliding back and forth, and it's that displacement in time of sliding back and forth that we will use to perform a Fourier transform to decompose that signal of displacement into the frequencies that are present, which will tell us something about the dynamics of that interface. Here are the traces of the interface. You'll notice if we look at the top here that there is an unperturbed line, which is the cylinder that you saw in the first several frames, and then the presence of antisymmetric modes, which have a node in the center, which is where it crosses that unperturbed interface. And you'll notice there are also traces in this direction with the same antisymmetric mode. This is the fundamental mode for the system because the tank is closed. So as the liquid goes toward the outside, as the interface goes toward the outside of the tank, there's less liquid present in that section of the tank, which means that the liquid has to go somewhere, and so the liquid comes down toward the inside. As we increase the perturbation frequency while maintaining the same rotation frequency. So the tank is spinning at the same rate, but the sliding along the track is increased from 1.5 times per second to 3.5 times per second. You'll notice that we see the same as before, the unperturbed, and then we see lines here which relate to the antisymmetric modes. But we also see the appearance of some two-node symmetric modes. All of these modes are superposed onto each other, but this is a clearly qualitatively different response of the interface at the higher perturbation frequency. Viewing from the axial camera, you'll notice the appearance. So we're looking through the bottom or top, depending on how you look at it, of the tank. You'll notice the appearance of this circle here, which is where the interface impinges on the gasket at the top. And then this wild behavior is the distortion of the view through the liquid layers and the refraction of the light through those interfaces. This is difficult to use for the axisymmetric views, or rather to understand about the axisymmetric modes, although we can see that there's some displacement of that interface meeting the gasket at the top of the tank there, and some slight departures from axisymmetry, which is to say that the interface, as we can see it from this view, is mostly circular, which shows that it's axisymmetric, where the displacement that we're viewing from the radial camera is the same in every position around the circle of that cylinder. We had accelerators mounted both on the sliding tank assembly as well as on the payload itself, so we could decouple the plane vibrations and gravitation from that of the perturbed signal. Here you see that in the parabola, this is time on the x-axis and the acceleration level on the y. And so you can see that as we enter the parabola, the acceleration drops down from higher g to about 2 to 3% of terrestrial gravity. And then we decompose that signal, we decompose the relative inertial signal between the two IMUs to acquire the acceleration imparted to the tank and at what frequency. So here we have frequency on the x and amplitude of that, each of those frequencies, which were extracted through fast Fourier transform of the relative IMU signal. And very simply, we get the dominant frequencies of the perturbation at 1.5, 2.5, and 3.5 hertz for each of the three parabolas analyzed here. Importantly, there's relatively low signal to noise, especially on the first parabola, which muddies the signal a little bit, although you will see that we can still extract some modal shapes from the interface analysis. So here we are, fast Fourier transform applied to each of these pixel rows. As I described previously, what that means is that I'm taking the displacement in time of each pixel row of this interface and then decomposing that through fast Fourier transform to extract the dominant frequencies to understand at what rates those positions of the interface are being perturbed back and forth. So here we have the frequency of that interface on the x and each of those rows. So this y-axis is the same as this y-axis for each of these pixel rows. And you can see that there's clearly there are clearly modes appearing at 1.5 or 1.3 and 5.1 hertz, which is the lower of which is very near the 1.5 hertz of the perturbation that we're seeing. And then you'll notice that there is a darker region in between the appearance of these modes. And each of these is a single node mode, which is reminiscent of the antisymmetric modes that we saw with the traces previously. Going to the next parabola, we have the same rotation rate at 3.2 hertz, but now the perturbation is increased to 2.5 hertz. And then again, we see the appearance of anti-symmetric modes, each with a single node at the center here at 2.2 and 4.6 hertz. And then as we go higher, we see the appearance of modes with more nodal crossings. Here you can see there appears to be a symmetric mode with two nodes at 6.9 hertz. And interestingly and importantly, each of these is within 0.1 hertz, an integer multiple of the fundamental 2.3 or so hertz frequency. That's very close to the 2.5 perturbation, which is what we would expect from the analytical solution for this, because the perturbation displacement is high enough that we're in a very nonlinear regime. We would expect to see higher harmonics of that fundamental perturbation frequency. And the same is true at the higher perturbation rate of 3.5 hertz in the next parabola. Again, an antisymmetric mode with a single nodal crossing here at a 3.1, or relatively close to what appears to be a fundamental frequency of 3.2, which is close to 3.5. And then as we go higher, we see the emergence of more nodes. So this 6.4 mode appears to have two nodes, and it appears to be it is an integer multiple of 3.2 as a fundamental frequency. So this FFT analysis shows us the presence of higher harmonics, would appear to be higher harmonics of fundamental perturbation frequencies. So next steps for this experiment will be to increase our resolution in both spatial and temporal regimes on our sensors, including the accelerometer and cameras, as well as to study the free response of this interface, which is to say the response of the interface without a driving frequency. And then to continue our work to derive the analytical solution to this model and validate that against the experimental results. So that's all for now. Thanks very much.